Good day, everybody. This is Mike Van Giem at Hammond Power Solutions. Thank you very much for attending our webinar today on active versus passive harmonic filters. This webinar has been approved for IEEE CE credits. In addition, I'd like to introduce Sanella Legata, who is one of the panelists. Sanella is our product manager in charge of all of our power quality products. And I'd also like to introduce our main presenter today, Bob Ellis. Bob has more than 30 years of experience with variable frequency drives and power quality. He is a professional engineer in the province of Ontario and a senior member of the IEEE. Bob has authored peer-reviewed papers on applying VFDs, harmonic modeling, and solving real-world power quality problems. I would like to welcome Bob to begin his presentation. Bob Ellis.
Thank you, Mike. So just to start off the presentation, I wanted to get into what is power quality. So electric power quality is the degree to which voltage, frequency, and waveform of a power supply system conform to established specifications. Good power quality can be defined as a steady state voltage that stays within the prescribed range, steady AC frequency close to the rated value, and a smooth voltage curve waveform that resembles a sine wave. Consider power quality as the compatibility between the electric supply and the loads that are plugged into it. Let's face it, almost everything runs on electricity, so the quality of power is important. For utilities, poor power quality can result in customer dissatisfaction and revenue loss. For customers, lack of power quality can result in costly production and equipment losses. If the power quality is outside an acceptable envelope, electrical devices can malfunction, trip offline, or fail prematurely. IEEE defines several main power quality issues, including blackouts, voltage sags, voltage spikes, harmonic distortion and voltage notching, voltage unbalance, and power factor. There's also a reflective wave issue, but this affects the output of a VFD to the motor and not the power system. There are numerous products to address these power quality issues, such as active and passive harmonic filters, line and load reactors for VFDs, drive isolation transformers, and DVDT filters. These are the tables from IEEE 519 that detail voltage and current distortion limits. This presentation is focused on low voltage systems less than 1,000 volts, so voltage distortion is limited to 8%. The current distortion limits depend on the ratio of short circuit current to maximum demand load current, but often the limit will be 5% or 8% total demand distortion. Harmonic distortion is a distorted voltage or current sine wave. There are many causes for harmonics that all involve nonlinear loads. Nonlinear loads convert AC power to DC power and include variable frequency drives, computers, UPSs, and lighting power supplies. This distortion is shown in the graph. The utility provides the large, perfect blue sine wave. The system's nonlinear load adds the multicolored, smaller, high-frequency sine waves, and this results in distorting the power system sine wave to the orange line. This distortion can cause overheating of cables and equipment, loss of efficiency in electrical machines, electromagnetic interference with communication systems, and nuisance tripping of thermal protective devices, to name a few of the most common issues. While there's a number of devices that address power quality in a power system, I am going to primarily focus on passive harmonic filters and active harmonic filters. These products are an effective way to reduce harmonics, but there are differences between them that I will point out. The presentation will also address factors that affect which product is better suited to a particular application. The main devices that are going to allow compliance with IEEE 519 recommendations are passive harmonic filters or active harmonic filters. This diagram shows that a passive harmonic filter is connected in series at the input to a VFD. so the components have to be fully rated for the VFD current. By contrast, an active harmonic filter is connected in parallel with the power system, so the components do not have to be rated for the full VFD load. The purposes of passive harmonic filters are to reduce harmonics and improve power factor. The passive harmonic filter can generally achieve compliance with IEEE 519 recommendations. It's a passive device in that it consists only of reactors and capacitors. Unlike an active harmonic filter, it does not have any power electronics. Passive filters that are predominant in the market are termed as broadband harmonic filters, since they reduce a number of harmonics, such as the 5th, the 7th, 11th, and 13th harmonics, and not just one specific harmonic like a single tuned harmonic filter. The source side reactor helps to keep harmonics from the power system from flowing into the filter. A well-designed broadband harmonic filter will not cause a resonance. Resonance occurs when one or more harmonics produced by a nonlinear load aligns with the natural frequency of the power system. Natural frequencies are created by the combination of system inductance and capacitance. This passive filter illustrated here has a shunt reactor that is rated for the full VFD current, which makes it very robust, and there is no need to fuse the shunt circuit. The shunt circuit with the reactor in combination with the capacitor is what shunts the harmonics that are produced by a VFD or other harmonic producing source away from the power system. So very little harmonic current gets back into the power system. So this is an illustration of typical passive filter performance. The black waveform shows what the current typically looks like at the input to a VFD without a filter. So this might be what the waveform would look like if you just had, say, a line reactor on the input to a VFD. Then the green waveform shows the current with the passive filter, and you can see it's very close to a sine wave, just some slight variations from a sine wave. So then the bottom graph shows a typical performance of current distortion, how it varies with VFD loading. The current distortion will increase slightly as load decreases, but the bottom line is that it will meet IEEE 519 recommended harmonic levels, regardless of what the loading is in the VFD. Another method to mitigate harmonic currents that are produced by three-phase sources is to use an active harmonic filter. Active harmonic filters are very similar to variable frequency drives in that they use IGBTs, but rather than power motors, they are designed to inject harmonic currents which are equal to but opposite the system harmonic currents to cancel out the harmonics. Active harmonic filters are designed to meet IEEE 519 recommendations and are usually combined with line reactors or DC-link chokes in the variable frequency drive. Active harmonic filters can compensate for multiple three-phase nonlinear loads. Single-phase nonlinear loads like computers and chargers must be mitigated with other devices like harmonic mitigating transformers. Active harmonic filters can also correct power factor to near unity and balance three-phase system currents. Active harmonic filters can address harmonics and power factor for an entire facility, one motor control center, or just one individual piece of equipment. A good comparison for active harmonic filters is noise-canceling headphones. With noise-canceling headphones, to cancel the lower frequency portions of an audible noise, like jet noise when you're on a plane, noise-canceling headphones use active noise control. They have a microphone that measures ambient sound. A small speaker generates an audible waveform that is exactly equal to but out of phase with the ambient sound to cancel out the undesirable noise. So the headphone's microphone acts in the same way as the active harmonic filter's current transformers. Rather than using speakers to generate an equal but opposite noise, active harmonic filters generate currents equal to but opposite harmonic currents produced by VFDs or other nonlinear loads. Here's a diagram To illustrate how the active harmonic filter works, the unit uses highly accurate current sensors to continuously monitor the current harmonics and instantly creates the current flow from its IGBT-based output module to make the resulting line current harmonic-free, balanced, and at unity power factor. Note that while an active harmonic filter can correct for power factor, it may be more economical to correct for power factor using capacitors if that is its sole purpose. Be forewarned, though, that power factor correction capacitors attract current harmonics, which can damage and destroy the capacitors if the harmonics are not mitigated. An active filter is connected in parallel with the nonlinear loads, as I was saying earlier, and typically used in conjunction with line reactors placed at each VFD. So in this illustration, there are 3 VFDs and 1 active harmonic filter is compensating for the harmonics produced by those 3 VFDs. This is sometimes less costly and more flexible than using passive filters in series with each of several VFDs. Line reactors help mitigate a portion of the current harmonics for less cost per amp than an active harmonic filter. But the line reactors cannot mitigate the total harmonic current distortion to below 5%. For that, the active harmonic filter is needed. This chart details some of the differences between passive and active filters. Active harmonic filters offer some advantages over passive filters, including better performance over a wider range of loads. One active filter can cover multiple VFDs. This is very advantageous when larger numbers of smaller VFDs make passive filters impractical. And active filters are wired in parallel to the loads so that the load can continue to operate even if there are issues with the active filter. If there are a small number of VFDs or the VFDs total less than about 100 horsepower, then passive filters will be the most cost-effective solution. The biggest disadvantage of active harmonic filters compared to passive filters is the initial cost, which is often higher unless there are a significant number of VFDs. Active filters will cost more than passive filters per amp of corrective current. So this chart gives a relative indication of what kind of current distortion you can expect depending on what type of mitigation method you use. So without using any form of mitigation on the input to a VFD, you can expect 60% current distortion. If you were to use a line reactor, and you expect somewhere between 35 and 44% current distortion. If you have a 5% line reactor, it would be on the order of 35% current distortion. And if you have a 3% line reactor, it would be more like 44%. So the real improvement in harmonics comes with passive and active harmonic filters. The current distortion with a passive filter will typically be in the range of 4 to 8%, and the current distortion for an active filter will generally be less than 5%. But it should be emphasized that both the passive and active harmonic filters are designed to fully comply with IEEE 519. There's a lot of information in this chart. Here are some of the main takeaways. A line reactor or a passive harmonic filter does not allow you to change the voltage, but transformers do. Line reactors, isolation transformers, and passive or active filters are effective on 3-phase harmonic sources, but not on single-phase sources. In order to achieve significant reduction of harmonic currents, you need a passive or active harmonic filter, and that will not be achieved with a line reactor or isolation transformer. Line reactors or transformers will not correct the power factor, but passive or active filters will. Line reactors, transformers, or passive filters are geared for a single VFD. Active harmonic filters are suitable for multiple VFDs. Reactors, transformers, and passive filters are series devices. If they fail, this will cause downtime on the VFD. An active filter is a parallel device. It can fail with no impact on operation of the VFDs. Line reactors are the smallest device you can use to mitigate harmonics, and transformers are the largest. And again, there's quite a bit of information here, but I just wanted to focus on a few key points. Transformers limit current in the event of a fault. Other devices do not. Active harmonic filters have built-in power quality monitoring and communications capability. Other devices generally do not. Line reactors and transformers are generally stocked, whereas passive or active filters often are not. Transformers provide electrical isolation, but other devices don't. Active harmonic filters are not effective at reducing voltage spikes, but other devices are. Okay, so now I'm going to go through some real world type examples and try to illustrate where it might be best to choose active harmonic filters and where it might be best to choose passive harmonic filters. So in this example, we have 12 50 horsepower VFDs. Each of these VFDs run cooler units in a HVAC system. 9 of the VFDs at most operate simultaneously. 3 of the VFDs are for backup capability only. In this case, harmonic levels need to meet IEEE 519 recommendations at the point of common coupling. So this just illustrates on a one-line diagram. We've got 12 50 horsepower VFDs. They're 40 volts fed by a 40 volt MCC bus, 12 50 horsepower motors. So the first way to tackle this one would be to use a passive harmonic filter for each of 12 VFDs. Since any of the VFDs could run together, each one needs to have a filter. Each filter would be rated for 50 horsepower or 61 amps. There might also be a need for filters to have capacitor contactors. The capacitor contactor switches the capacitor of the circuit when the VFD runs at light load to avoid a leading power factor. The other option in this case would be to use a single active harmonic filter sized for simultaneous operation of 9 VFDs, since 3 of the 12 VFDs are redundant. We can use an Excel-based sizing tool to determine what the size of the AHF active harmonic filter should be. So this is a screenshot from an active harmonic filter sizing tool. You enter the total nonlinear load horsepower, which in this case is 450 horsepower, which is 9 times 50 horsepower, as well as the percent impedance of DC bus chokes or line reactors that are used with the VFDs. So in this case, we have a minimal DC choke and a 5% line reactor. You can also put in linear loads such as motors that run across the line or resistive loads like electric heating. So when we plug in these numbers, it estimates that we need about 147 amps of corrective current. So we would select a 150 amp active harmonic filter. So the single active harmonic filter is likely a better choice in this case. Instead of 12 passive filters, there would be 1 active filter sized for 450 horsepower or a 150 amp active filter. The AHF should have a lower capital cost and installation cost because you have 1 active harmonic filter and 1 installation, whereas with the passive harmonic filters, you have the cost of 12 individual passive filters as well as the installation cost for those filters. And in both cases, they're going to meet IEEE 519 and address any power factor concerns. Okay, so in this second example, there are 3 100 horsepower VFDs and motors that run compressors. All 3 VFDs can run close to full load. The aim is to avoid ill effects from harmonics and to meet IEEE 519 recommendations. There's no need for monitoring and there's no generator backup power. And this is just the one-line diagram for this case. 300 horsepower VFDs and motors and fed from a 40 volt bus on the utility system. So here is an example. We have an Excel-based passive harmonic filter simulation tool to give an idea of what passive filter to select and what you can expect for harmonic current distortion. So in this case, we've got 300 horsepower VFDs. We enter those as the nonlinear loads 1, 2, and 3. So it tells us which filters to select. The red waveform shows is what the harmonics would be without mitigation. And then the green waveform shows the mitigated waveform with the passive filter. So you can see with the green waveform that it's very sinusoidal, the harmonics are low. And it also shows that with a 5% line reactor, you would have on the order of 32% current distortion. But if you introduce the passive filter, the current distortion is just over 4%. And in the lower right portion, there is a frequency spectrum which shows the percentage of current harmonics, the harmonic orders, and the percent of those harmonics. Okay, it also illustrates that the power factor will improve. With a line reactor, you'd have a power factor of around 0.96, and with the passive filter, it would improve to about 0.98. So the other option is to use one active harmonic filter. And again, we use the active harmonic filter sizing tool to determine what size is required. So we have a total of 3 100 horsepower VFDs, so we enter that as 300 horsepower as the total nonlinear load into the spreadsheet on the left, top left. We're trying to achieve current distortion, let's say, of 5%, so acceptable TDD is 5%. And this basically shows that approximately 98 amps of corrective current are required. And that would result in choosing a 100 amp active harmonic filter. So in this case, the economics will likely dictate that 3 passive harmonic filters is likely the better way to go. The capital cost for the passive filters should be lower. Again, it may be warranted to add a capacitor contactor to each passive filter if the VFDs sometimes run at light load. Both the passive and active filters will keep harmonics to a reasonable level and allow compliance of IEEE 519. So the selection is primarily driven by economics. So in this last third example, it's a large distribution warehouse. In this example, there's numerous 5 horsepower and 10 horsepower VFDs. There are 6 25 horsepower VFDs that are used for the air conditioning system. And there's many small VFDs up to 3 horsepower that are used for conveyors. So when everything's added up, there's a total of 555 horsepower of VFD load, which is split evenly between 3 MCCs. IEEE 519 recommendations need to be met. So the first option we could use is to have separate passive harmonic filters for each of the VFDs in the 5 horsepower to 25 horsepower range. This would mean 42 passive harmonic filters. And in a lot of cases, passive harmonic filters are not readily available for loads under 5 horsepower. So these VFDs would not be filtered. Either that or some of the VFDs would have to be lumped together on a single filter. The other option would be to use a single active harmonic filter for the total VFD load, or to use 3 active harmonic filters, 1 per MCC. Again, we can use our active filter sizing tool to determine the current rating required. We know that the total horsepower of the VFDs is 555. We've got minimal or no DC link inductance. We have a 5% line reactor. And we're trying to get the current distortion acceptable TDD to 5% and a 0.95 power factor. So it's determined that you need about 182 amps of active filter current to address the harmonics and power factor. So we would choose a 200 amp active filter. So the third option would be to use an active harmonic filter for each MCC. So essentially you'd have a third of that 555 horsepower VFD load on each MCC. So you've got a third of 555 horsepower or 185 horsepower in total nonlinear load. And the same parameters that you're trying to achieve for the harmonics. And it says that you need about 60 amps of corrective current. So in this case, we would choose a 100 amp active harmonic filter, which is the closest size available above the 60 or 61 amps. So in this case, passive harmonic filters would not be practical because you would have to have at least 42 passive harmonic filters. The capital cost would be high and the installation cost would be quite high. And passive harmonic filters are not practical, usually below 5 horsepower. A single 200 amp active filter at the service entrance would cost significantly less than the 3 active harmonic filters, the 3 100 amp active harmonic filters, and it would cost quite a bit less than the passive harmonic filters. Okay, so hopefully these 3 examples have pointed out the factors that go into making a decision between active and passive filters. That really concludes the formal part of the presentation. And I would like to open the floor to questions. Thank you for your attention.
Thank you very much, Bob. Once again, this is Mike Van Geen from Hammond Power Solutions. I did have one question that popped up so far, and what is the largest rating of active harmonic filters offered by Hammond? Our largest active harmonic filter is currently 300 amps, although we are working on some larger sizes. And also note that we can parallel up to 10 different harmonic filters. So we can parallel up to 10 300 amp filters together, which would give us 3,000 amps of harmonic correction. I do have a question here. What can be done to prevent voltage spikes in an active harmonic filter application? So voltage spikes are kind of outside of a lot of our products. Typically, you would have some type of surge protection device. We do offer surge protection devices as an option on our transformers, along with lightning arresters, which is a very common option on our larger power transformers. So that would help protect the active harmonic filter. But again, in a lot of cases, people will probably use a separately mounted surge protection device. Hope that answers your question.
Yeah, I would agree, Mike, that you need to use some form of transient voltage surge suppression separate from the active filter.
Okay. Bob, the next question is, are these filters true 600 volt or are they 480 volts with an auto transformer?
So good question. They are in fact a 480 volt rated device, and we use an auto transformer at the input to achieve 600 volts. And that's something that we will work on in the future. We would like to offer a true 600 volt device, but the efficiency is still high. There's not too much losses with the auto transformer, and the installation footprint is still reasonable by putting in the auto transformer and the active harmonic filter.
Thank you, Bob. Next question. Can an active harmonic filter be used without a line reactor, or is a line reactor always required?
So essentially, you need to have some kind of impedance in the VFDs or other nonlinear loads that are used with the active filter. So if it's VFD loads that we're using here, then you either have to have a line reactor or a DC choke in the VFD. So you don't have to have both, but so if there's no line reactor, then you need the DC choke. If there's no DC choke, then you need the line reactor.
I'd like to add that many small VFDs, depending on the manufacturer, might be 20 horsepower and below or 10 horsepower and below, may not contain a DC link choke.
Yeah,
Bob,
that's fair.
same question. Can a passive harmonic filter be used without a line reactor?
Yes, in fact, it's recommended to not to use a line reactor. What happens if you use a line reactor in combination with a passive filter is that you may result in excessive voltage drop. So then the excessive voltage drop could lead to a reduced amount of torque being available from your motor to your load. So it is not recommended to use a line reactor and a passive filter together.
Thank you. Next question. When we are modeling the harmonic reduction with an active harmonic filter, I'm going to go to one of our slides here, Bob. Do we include the reduction of harmonics due to a line reactor or a DC link choke when we do our modeling for active harmonic filters?
Yes, if you look towards the upper left where it says customer input, there's a line for percent DC choke reactance, and then the next line is percent input line reactance. So it takes into account how much DC choke impedance you have and how much input line reactance you have to determine what the current is that's required from the active filter.
Next question, does Hammond deal with the noticeable audible noise on utility transformers with an active harmonic filter operation? Has this been evaluated? And I can actually answer that. We have not evaluated audible noise. I would comment too that the audible noise on transformers can come from a number of sources. And while people sometimes assume that the audible noise on a transformer is caused by higher frequency harmonics, it is often caused, or the major components of it are other things. Most transformers, the major reason for the hum is just simply the core vibrating. The core will be vibrating at twice the frequency of 60 hertz. And that's by far the biggest component of the noise of a transformer core. The higher frequency harmonics are a component, but typically much smaller, and oftentimes audible noise may be caused by something other, or at least the major component of it is caused by something other than harmonics. However, again, we have not evaluated that question specifically. Bob, would you agree with that? Or any questions there?
Yeah, I agree, Mike.
All right. What filters are recommended for voltage suppression, I believe is the question, at a high voltage level, 25 kV class? And for the purpose of this discussion, we're really talking about a 600 volt class and below. However, I will say that from our own experience, typically customers will specify things like lighting arresters and or some type of surge suppressor, depending on what type of spike you are trying to mitigate for those larger medium voltage power transformers. We don't, however, offer or have a standalone solution. Typically, either the lighting arresters or spokes or surge suppressors are integrated directly with our transformer. Hope that answers your question. Bob, can you elaborate on the difference between a DC link choke and a line reactor?
Yeah, so a line reactor is connected on the input to a VFD, so between the VFD and the power system. And a DC link choke, there's basically two parts to a VFD, the rectifier and the inverter. So the rectifier is on the input to the VFD that converts AC power to DC power. And then the inverter converts that DC power back to AC power at variable frequency for the motor. So on that DC circuit between the rectifier and the inverter is where the DC choke is connected. So you can have one coil in one side of the DC link, or two coils, one on each the positive and negative legs of the DC link.
Thank you. I'd also add that a line reactor is typically a three-phase device, and a DC link choke is essentially a single-phase device because it's connected just straight to the DC bus of the VFD. Next question: does Hammond have an auto translineator with a passive harmonic filter that can transform the voltage between the VFD and the supply? I believe it's probably an autocorrect here, or autocorrect. You mean an auto transformer with a passive harmonic filter. For the most part, we don't offer that, and the reason for that is that we do offer passive harmonic filters in the most common VFD voltages in North America. By far, the most common ones are 480 and 600 volt. If you do need to transform the power, typically we would do that with possibly a drive isolation transformer before the passive filter, but not between the passive filter and the VFD. You could, if you don't need isolation, also use an auto transformer. However, auto transformers aren't necessarily inherently rated for the harmonics you might see, albeit the harmonics, in between it with a passive filter or active filter should be low. Would you agree with that answer?
Yeah, just to build on that, Mike, as Mike said, we've got standard harmonic filters available for 40 volts and 600 volts at 60 hertz. But if there's a special need out there, if you come across a different system voltage, in that 600 volts and below kind of thing, we can definitely look at it and design special filters. So if it's 600 volts, or let's say 440 volts, 50 hertz, 220 volts, 50 hertz. Like we can design filters for various voltages and frequencies. So there's no real need to change the voltage to the filter. We can just use a specialized filter for the application.
Bob, let's assume this. Let's assume we have a large facility. We have multiple passive harmonic filters throughout that facility. How would we, or can we, go about installing an active harmonic filter with the knowledge that some of the loads downstream will have passive harmonic filters?
It really shouldn't be a problem. I mean, it's really it's not something I touched on in the presentation, but there is something called hybrid solutions. So it may be sensible to sometimes to do a combination of passive harmonic filters and active harmonic filters. When it gets down to let's say a large number of small VFDs, it may be impractical to put a passive harmonic filter on each VFD. But if you have some significantly sized VFDs, you could put passive harmonic filters on those individual VFDs, and then any other harmonics from VFDs or other sources could be cleaned up by an active harmonic filter. But there's nothing particularly difficult about implementing that type of mitigation, and it's called a hybrid correction system.
A couple things with an active harmonic filter, we are concerned, not necessarily if there's passive harmonic filters downstream. We do need to know about them because it helps us with sizing the active harmonic filter. We are concerned if you have any power factor correction capacitors and where those are located in relation to the active harmonic filter. And I would also add that an active harmonic filter can do dynamic VAR correction. And if you need, it is an alternate method to use rather than power factor correction capacitors. However, saying that, it tends to be a more expensive solution per kVAR correction than using power factor correction capacitors. But in some cases, maybe if you just need a little bit or something like that, and you may have some extra capacity with a active harmonic filter, you may be able to get some additional correction with that, and maybe not even have to provide power factor correction. All right, well, thank you so much for attending this presentation. If anybody would like information on the products that we have, active and passive harmonic filters, drive isolation transformers, multi-pulse transformers, and such, please visit our website at www.hammondpowersolutions.com. It's all one word in plural. Solutions is plural. We do have all of our information there. We also have a configurator. We do have the active harmonic filter sizing tool that we've shown here. However, the passive harmonic filter modeling that we do, that's currently done within our system. So typically Bob Ellis would work with you if you want to do that type of modeling. Once again, we greatly appreciate your time and hope everybody enjoyed this presentation.
Thank you, everyone.